So in this video, we want to talk about interpreting area under a curve and trying to make sense of what the area under a curve tells us. So we've been focused a lot over the last few homeworks on calculating signed area under a curve. So let's say on the vertical axis, we have a rate of change as our output. So we'll call it Q prime. I'm just going to use Q to represent any quantity that's changing, so quantity. So we have Q prime, or dQ, change in Q, over dt, change in time. So the rate of change of some quantity Q. And down here I have the time axis, and the time units can be whatever you want them to be. So if I have the curve Q prime, so this is Q prime is just going to be some function. So here's my curve Q prime. What I can ask is, what does the area between the curve and the input or time axis represent? And what we want to remember is, if we're integrating over some closed interval, say from A to B, so we integrate over some closed interval from A to B, we know if the curve is Q prime, and we do Q prime, and this is a time axis, so we'll call it dt, we know that this integral from the fundamental theorem of calculus is going to give us the signed area under the curve. And we may have positive area where the curve is above the x-axis, negative area where the curve is below the x-axis. And the question is, if we use the fundamental theorem of calculus to calculate the signed area underneath this curve, what does that area represent or tell us? And I just wiped out my entire x-axis, or t-axis, time axis. See if I can draw it back in without reshooting the whole video. Okay, so we want to have a discussion about what that area represents. So dq dt, change in quantity over change in time, and it could be anything. It could be change in position over change in time, which is a velocity. It could be a change in height over change in time, dh dt. It could be the change in the number of candy bars, d bars dt. The change in the number of candy bars that a company produces per hour. Any rate of change. So let's suppose, for example, that it's a velocity, dp dt. And let's say that the velocity is measured in miles per hour. It's a rate of change, and we know that this integral right here, this definite integral, let's say we plug our velocity in there, dt, and we want to recognize that velocity is just change in position, dp dt, integrating over the time interval from A to B, times dt. So even though it's naughty, what we want to visualize is dt divided by t, dt being 1, and what you get is a dp, a change in position. And remember, this is a summation. This is just sigma notation as the number of approximating rectangles went to infinity. So this would be add up all of the changes in position. And if we do that, we get the total change in position. Total change in position. dp dt times dt. The dt's cancel. Change in position. Add up all the changes in position to get the total change in position. So we would call this the aggregated position. So we approximated area under the curve with rectangles. We let the number of rectangles go to infinity. If we were using right endpoints, we would have plugged in the time on the ith rectangle. The function would have had an output t sub I. And if we're doing velocity, I'm not good with my pen today. Time on interval I, comma. If I'm doing velocity, it's velocity at that time. And remember, to calculate this, we took the height, which in this case would actually be a velocity, height times the width, but the width would be a change in time. So we took a velocity times a change in time, and velocity is just miles, say, per hour. So it is the change in time. So hours times change in hours gives you miles. So if I have a velocity function, the area under the curve is going to tell me the total miles that were aggregated while I traveled at the different velocities I took on along the path. So bottom line is, when we have the area under the curve, it gives us the aggregated change. You get positive area, sometimes canceling with negative area, winds up giving you the total change that happened, the total change. So what was the change in Q? What was the total change in position? What was the total change in height? What was the total change in candy bars? Because in each case, each rate of change, when you plug it into the integral, it's going to get multiplied by a dt. And you're going to be adding up the change in bars, the change in height, the change in position, the change in, multiply it by dt, the change in quantity. So this leads to the net change theorem. So if we have an antiderivative of little f of x, then if we calculate the integral from a to b of f of x dx, and if f is an antiderivative of f of x, that means that f prime of x is f of x. So if we take the rate of change times the change, dx is the change in x, so take the rate of change of x, so this is df dx, and multiply it by dx, we're aggregating the change in the function f. So the net change theorem says, hey, if you calculate the definite integral of a rate of change or of a derivative, then the area under the curve, which is what this calculation gives you, the area under the curve, the signed area, is the net change that happened over the integral over which you are integrating. So in the next two videos, we're going to show examples of calculating the amount of change that happened using the net change theorem or small tweaks to the net change theorem, using the idea that the area under the curve of a rate of change is the amount of change that happens. It represents the actual change.